All right, so let's go ahead and compute a few more volumes. So let's start with that. So let's go ahead and look at this graph, the square root of x. Let's do that, and there. And let's try to compute the volume of the solid generated by rotating around the x-axis. So let's do that. Okay, so I went ahead and drew the graph of the solid that we obtain when we rotate around the x-axis, and let's pick a rectangle or a section here. Let's redraw that one a little bit. So if we cut a section here, what we obtain is going to be a cylinder of this form. So I'm going to move it over here. I draw it here on its side. Let's do it like this. There. All right, and there. All right, and so the thickness, you see the thickness is going to correspond to this right here. That's going to be my dx because I'm going to be on the x-axis. So I don't have to put it down here. That's going to be dx. All right, then the radius for this is going to be this line right here. And if you notice, that line corresponds to your y coordinate. So this right here is going to be y. So now the area of this disk, this is why they call the disk method, because you end up with a disk. The previous video we had a shell. This is called then the disk method. Again, as I told you, the names are not important because when you draw it, you end up already seeing the object. So the area of this disk is going to be pi r squared. The radius is y. Oops, y squared. And y is equal to the square root of x. So your dV, the differential volume, is going to be pi x, the area, A of x, times dx. That's the same formula we used when we computed our volumes by slicing, right? The dV, let me write it here as a note, we always wrote it as A of x dx. So that's the same situation we have here, except now our sections are just, when you cut infinitely many sections, are just circles, right? So that's why we're getting pi r squared as our area of a circle. All right, so now putting that together, we can integrate to the volume. Let's separate here and start all the way here so I have enough space. It's going to be the integral from 0 to 4, y 0 to 4, because those are my endpoints in the x coordinate, and I'm integrating with respect to x. So my endpoints are going to be on the x coordinate because the integral is with respect to x. That's just how we chose, or how we chose to look at the area or compute the area that then we revolve around the axis. So now that's going to be just pi x, and we integrate. That's going to be pi x squared over 2 from 0 to 4. At 0 is 0, so we're just plugging it at 4. We get 4 squared is 16. Divided by 2 is 8, so 8 pi units cubed. And that would be our first area. All right, let's do another one. Okay, so let's look at the cosine, for example. I just realized that my integral will have the cosine squared, and we haven't talked about how to integrate that. All right, I'll tell you how to do it anyways. So here we go. Exciting times. All right, so let's say we have the cosine between 0 and pi, and we're going to rotate it around. So what do we obtain? So more or less, we get a figure that looks like this. So let's go ahead and grab a rectangle here. And actually, let me just grab this vertical line. Then I'm going to draw the corresponding I have this activated, the corresponding circle, and then I have a differential of width that gives me then my dx there, the width of this of the disk in this case. So this is going to be a disk method again. So let's draw that disk around here. So there we have that, and then we do here, 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 and that's going to be the width of that is going to be dx. The radius, once again, is going to be the height y right here. That's going to be y, the y coordinate. And the area, let me change color because that's hard to see, I think. The area is going to be given by pi r squared, which is pi y squared, which in this case is going to be pi cosine square of x. This is where I had the difficulty, because when I set my equation for the volume, it's going to be the integral from 0 to pi, and you're going to say, wait a second, because now the function, when I draw my next rectangle, would be down here, because the function, remember, went and crossed down to a negative, and you'll say, now your integral will be 0. When, like, thinking about what we did in the areas. However, remember that cosine will be squared, so when you're doing this solids of revolution, whenever they're disk, whenever they have squares, you don't have to worry about it, because that square will take care of the sign. So it's kind of nice, actually. So I'm going to have pi, whoop, wrong color. So pi cosine squared of x dx. And to compute the integral of the cosine, it's kind of annoying that I chose that one, but it's okay. Let me continue here, down all the way back here. You're going to pull the pi out. You're going to go from 0 to pi, and then you're going to have to use a half-angle formula that people don't remember. When I teach pre-calculus, I always tell them, well, remember this one because you will need it. And so if you look at your formulas, this would be your half-angle formula. So that cosine squared becomes 1 plus cosine of 2x over 2, and then your dx. And now you can integrate each one separately. So the first one is just going to be pi over 2. Let me pull that over 2 outside. Integral of 1, that's just going to be an x. That's going to be evaluated between 0 and pi. Then plus, I still have that pi over 2, and I have the integral of this from 0 to pi, cosine of 2x. And here you need to do a u substitution, u equals 2x. What that's going to turn out, what that's going to do, is it's going to give you another 1/2 coming out. Let me evaluate this one though. When x is pi, you get pi squared over 2. And when x is 0, you get 0. So that's just going to be pi squared over 2. And then pi over 4, as I said. And then the integral of cosine of u du. I know I'm skipping the substitution. And then when since u is 2x, whenever actually, why am I doing that? Let me just write my substitution. U equals 2x, and then du is 2dx sorry, and then from that I get that the dx is 1/2 of the du, and that's what the 1/2 it came out here. All right, so when I evaluate at x equals to 0, I get u is 0, what I have here. And then whenever x is pi, I plug it in here, and u is 2 pi. And now I can integrate that. The cosine, the integral is just the sine. So I get pi squared over 2 plus pi over 4 of the sine of u evaluated between 0 and 2 pi. But the sine of u or both at pi 2 pi and at 0 is equal to 0. So that just gives me a pi squared over 2 for my volume rather. I think we can still do one more, but this one is going to be a little bit different. I'm going to pick my discs to go perpendicular to the y-axis. So let's go ahead and draw one of those. All right, so let's say now that we're going to have that square root of x, and I want to grab the area from 0 to 1, but on the y, so bounded by the line y equals to 1 as opposed to x equals to 1 as we had been doing before, and I'm going to rotate it around the y-axis, and you'll see why that's going to result in a disk. So we'll do that. Okay, so let's rotate it around. So if you grab one disk here, like so, I'm going to grab it and zoom. I'm grabbing the width or the thickness of that disk is in the y axis, so this is going to be a dy. We hadn't done one of those, had we? And now notice that here the radius is going to the x coordinate. That last line is pretty terrible, but let's say that is going to give you the x coordinate. So your radius is x. And so now change colors. The area of the face of this cylinder or disk is going to be given by pi r squared, where the radius now is x. But now think about it for 1 second, because x is not what I'm going to be integrating against. You see, I'm going to have to put a dy. So let me just write it so you see what the problem would be. So I would have the integral, I said, from 0 to 1. So 0 to 1. And then I would have pi r squared dy. So you're integrating in the y coordinate. You see your endpoints are from 0 to 1. You have an x. That's a problem. So what you're going to do here is you're going to square both sides to get your x. We're restricting ourselves to the positive x's, so we don't have to worry about there like an absolute value or anything like that. Well, x is only possible for positive to begin with, so we're good there, just taking the square on both sides. Now then I'm going to plug for x, I'm going to plug y squared, and so I'm going to be able to integrate it 0 to 1 pi, and instead of x I'm going to put y squared and then square again. So instead of x I'm just plugging that, and I'm having the integral from 0 to 1 of pi y to the 4th dy. And that's easy to do now. It's just going to be pi y to the 5th over 5 using your power rule between 0 and 1, which boils down just to be pi over 5 or pi fifths, because you plug y equals to 1, you get 1 there, minus when you plug 0, you get 0. So pi over 5 units cubed, if you will. All right, so that will do for this first approach to our disk method. Then we're going to do more examples. And we're gonna get to see some that are called the washer method, which is just the disk method, subtracting two volumes one from the other. But we'll do that in the next video. So until then, I'll see you in a little.